Hello y'all, this is for all of you CMASers that decided to ditch my class and take that stupid standardized test. Instead, shame on you. Don't tell anyone I said that. This video is about voltage. It's what we did on block day. Voltage, it's simply electric potential energy. I think the AP videos give you a really great understanding of like how to calculate it, but they don't talk about what it fundamentally is, or why am I adding these things together, which I think is a shame, and that's the kind of whole point of this video. It's talking about voltage. Voltage is electrical potential energy. We can also just call it potential. You'll see that everywhere, that we're going to say, oh, what's the potential of this battery? And what voltage is fundamentally is just how badly electrons want to get from point A to point B, which in this case, it's how badly electrons want to get across this wire. I can take my voltmeter, and there's a bunch of electrons here and not a lot over here. So they're going to repel each other. They're really going to want to get across this wire. And as you'll see, it really depends on two things. This anode is pushing with 12 volts, and this cathode is sucking with 9 volts. So when I put my voltmeter up, these two numbers get combined. I get a total voltage of 21. There's 21 volts, a potential of 21, and that's how badly these electrons want to get across here. You've probably seen 12-volt batteries, 9-volt batteries. You've seen power lines and it says hazardous, really high voltage. Why is that bad? Well, if you're next to a high voltage line, those electrons want to get from point A to point B, which, if you're close enough, point A is the wire, and point B is through your body, through the heart, and into the ground. If it's really high voltage, they really want to arc through the air and jump through your body and kill you. But the reason they have to be high voltage is we're sending these electrons miles and miles away to give everyone power. So we need high voltage because we need those electrons to really want to get across those miles of distance that they have to travel. So we're going to look on, or we're really going to focus on how to calculate voltage. Big idea. Positive voltage is favorable. Negative voltage is unfavorable. And like we just saw, it is a combination of how hard the anode is pushing and how hard the cathode is pulling. So this is pushing with plus 5 volts. This is pulling with negative 2 volts. That's unfavorable. This is the bad cathode. It's pulling negative 2. We don't, it's not great. So we only get a voltage of 3 when we combine 5 and negative 2. So therefore, it's low voltage, and it's mainly because of this cathode that's not pulling very hard. Now, this is a potential energy, and it's just like we saw in gravitational potential energy. I'm going to go back to my ball example, where I had the ball in the classroom above the gym. Now, just because something has a negative voltage, that doesn't mean, like, there's some misconceptions. People will say, oh, this cathode is actually pushing off electrons instead of sucking them in because it's negative. That's not true. People say this battery won't work because this is negative voltage. That's not true. So we go back to the ball example. The ball could be right here, and it has negative 2 potential energy. In this case, it was gravitational potential energy. Now, the ball can absolutely still fall. It absolutely still has potential energy in it. It just means it has 2 less potential energy than this random arbitrary 0 point that we set, which is what you'll see. So we go into the question of, well, how the heck do we actually, where does this plus 5, where does this negative 2 come from? And it's from, you'll pull them from a table. It's called a reduction potential chart. So here's 2 tables. This is our standard reduction potentials and standard oxidation potentials. So it's really just the voltage of things that are being reduced. So I have a ton of half reactions. I can look at anything. If I've got bromine gaining electrons, that's being reduced to become 2Br minus, that half cell will have a voltage or a potential of 1.07. Chromium can take an electron. That's going to have a voltage of 0.41. And if we remember, positive for voltage is good. So all this stuff up here are good cathodes because these are the most positive. You get better cathodes up here, worse cathodes up here. I go back to chromium. Now chromium here, gaining an electron, is negative 0.41 volts. And we go back and we see, oh, that doesn't have, misconception students will say, oh, I can't use that as a cathode because it's negative. Absolutely not true. You can use this as a cathode. It's just kind of a crappy cathode. And it's negative. The only reason it's negative is because this hydrogen reaction is what we arbitrarily set as 0. And it sucks electrons minus 0.41 worse than this arbitrary 0 point. Still can be a cathode. So these are for reduction reactions. There's also a chart I've made for oxidation, standard oxidation reactions, which are things giving off electrons. This will be your anode. So silver turning into silver plus an electron, minus 0.8 volts. So silver doesn't really like giving off electrons. That's a negative voltage. Still can. All of our anodes up here are worse. All of our anodes up here are better. More positive voltage. Now, one thing I'd like to recognize about this chart, if we look at reduction potential, we got like fluorine, cobalt, gold, chlorine. Fluorine, cobalt, gold, chlorine. These two charts are the exact same chart, just flipped. After this chlorine reaction, we got water turning into oxygen and hydrogen. Here we got oxygen and hydrogen turning into water. These are literally the exact same charts, just flipped. And the voltages are flipped as well. So I go back to my silver reaction right here. Silver gaining an electron is positive 0.8 volts. Same exact spot, but now it's the oxidation reaction. Silver giving up an electron is negative 0.8 volts. So it makes sense. If you're really good at taking in an electron, it makes sense that you'd be pretty bad at giving that electron back up. So to find the voltage of a battery, it's pretty straightforward. We have to determine the half reaction of the cathode and get that potential from the reduction potential, because the cathode is reduction, and determine the half reaction of the anode. Get that from the other chart, and then you simply add the voltages together. So here's one question. We got a battery. It's made out of potassium metal in one half cell and an iron chloride solution in the other half cell. So it's really potassium and iron. First hard question we're going to have to look at is which half cell is the cathode and which is the anode. So we'll remember we got potassium and we got iron. So I'm just going to look for this. I am on my reduction chart, which is gaining electrons. So potassium is, I think it's all the way at the bottom. Here's potassium, negative 2.92, almost negative 3 volts. Really crappy cathode. Does not like gaining this electron. So let's just keep that information floating in our head. Potassium is a bad cathode. Here is iron. It's FeCl3, so it's going to be iron 3 plus, gaining an electron. Much better cathode. So let's put those two pieces of information together. Iron is a good cathode. Potassium, I'm looking at the oxidation chart now. So the reaction's flipped. Potassium, when it gives up that electron, instead of when it gains the electron, it's negative 2.92. Now it's giving up the electron, positive 2.92. Potassium is a great anode. Really likes giving up electrons. So potassium is our anode. It's going to push with a voltage of 2.92. Iron 3 plus is going to be the cathode, and this is what's going to be taking an electron, so we're going to use this reaction. That is going to be a voltage of 0.77. So we can write those half reactions. I'm not going to write the half reactions out, but the iron was taking in electrons right here. That's 0.77. And the potassium, when it gives up these electrons, is positive 2.92. And then we just simply add those together. 0.77 plus 2.92. So total voltage should be 3.92. Boom, easy enough. We're going to practice this with 2 practice problems. We've got voltage right here. What this slideshow wants you to do, for each battery we've got to figure out what's the anode, what's the cathode, write the half reactions, which I'll leave it up for you to do. And we have to put an arrow showing which way the electrons are flowing, write the voltage of each half cell, and calculate the total voltage. So we will look at our first problem. I've got lithium and fluorine. Now, I can look at both these charts for reduction and, oh my God, and oxidation. For right now, and for most of the time, you're only going to be given the reduction chart. So they'll only give you this chart, and you just have to know that the oxidation chart is everything flipped around. The reactions flipped around, and the sign of the voltage flipped around. So let's look at our reagents. I got lithium, I got fluorine. Top of the list, fluorine is at the top of the list for reduction. Again, red cat, reduction occurs at the cathode. So this is a great cathode, very top of the list. Amazing voltage. So everything else is going to be a worse cathode. I'm just going to write in right here. Let me make sure this is good. Font size. So this is going to be the cathode. And it's going to give up electrons. With 2.87 volts is what the chart gives me. So positive 2.87 volts. We look for lithium in here, and lithium is at the complete bottom of the chart. So lithium is a terrible cathode. Negative 0.3 volts, really doesn't care to accept that electron. However, if we flip this entire chart around, solid lithium giving up an electron is a really great anode. That's going to be a plus 3.05. Did I say this was going to? Okay, I apologize. Fluorine is going to accept electrons. That is my, yeah. Oil rig, reduction is gaining. This is a good reducing, so fluorine is going to accept those electrons with plus 2.97 volts. Lithium is going to give up those electrons. So we're going to flip this reaction. I'm going to say lithium turns into lithium plus and an electron. Gives up electrons, and I'm going to flip the sign of this as well. That's actually plus 3.05 volts. So this side is going to be the anode. This is going to give off electrons with positive 3.05. And then we simply add those together. Lithium is pushing with 3.05. F2 is polling with plus 2.97. That gives me 6.02, which is a good number. And then finally, it says to draw an arrow. So I'm going to put a big red arrow. Let's make this a lot bigger, 12 points, bright red. So electrons are going to be given off from lithium and accepted by fluorine. That's going to be the direction of electron flow. Electricity will flow from here to here in the wire. And I think that's everything. All right, second and final example. I've got silver and I've got iodine. So we're going to look for these on the reduction chart, and I'm gonna actually write these reactions. So here's silver gaining an electron, and that's 0.8 volts. So Ag plus E minus Ag plus E minus goes to silver. Oh my God. With plus 0.8 volts. And the other reaction is going to have to do with iodine. Now iodine's pretty high up, reduction chart. Iodine's pretty high up on the reduction chart as well. Silver's right here, iodine's only 3 below it. I2 plus 2 electrons. Goes to 2I minus. And that's going to be 0.53 volts. Now, we have a bit of an impasse. Both these things are good cathodes. They both have positive voltages on this reduction chart, this cathode chart. So the question we're going to ask is, which one's going to be the cathode? And that's simply whichever one's the better cathode. And silver can push electrons harder than iodine can. So silver's going to say, suck it up, iodine. I'm going to push electrons. You're going to take them in. So silver will leave. I'm going to write that this is the cathode. And then iodine, since it's the anode, I'm going to label that as well. We're going to have to flip all this. So it's going to be 2I minus is going to give off electrons and turn into I2 minus. That positive 0.53 volts is going to turn into a negative 0.53 volts. And that's how I know it's not a great anode, because it's pulling with negative 0.53 volts. It's going to actually hurt our total voltage. But that being said, this is still a perfectly working battery, completely fine. And we just add the voltages together. Silver is pushing with plus 0.8, and I'm going to add a negative 0.53. Iodine is sucking with negative 0.53. Total voltage of this battery is 0.27. Boom. Oh, and then the anode gives up electrons. It's iodine giving up electrons. That's the reaction. Cathode is sucking them in. So electricity is actually going to be flowing this way in our wire. Electrons will be put off here and sucked in here, and that is good to go. All right, last but not least, I have an AP FRQ. Let's read it together. Student sets up a galvanic cell, just like the ones we've seen, has an electrode of silver immersed in silver plus ions, and an electrode, which is the solid chunk of metal, of chromium, immersed in a solution of chromium ions, as shown in this diagram. Question A, the student measures the voltage of the cell above and discovers that it is 0. So this voltmeter is reading 0. Identifying the missing component of the cell and explain its importance for a non-zero voltage. What is missing is the salt bridge. If we go back to here, one of these, there we go. If we go back to here, we need a salt bridge. And the entire reason we need the salt bridge is as the battery runs, as we can see here, as the battery runs, we're going to create charges in these half cells that don't get balanced out, so to speak. So if this battery were to run to completion, here, let me start it from the beginning. Like I got a battery with lithium and copper, plus we run it to completion, all the lithium gives up its electrons, all the copper takes it in. We have created a tremendous amount of positive charges here and a lot of negative charges here, and the battery just won't do that. Like the battery won't work. We need to balance those charges out. So for the AP question, it's missing a salt bridge, and all the salt bridge does is it balances ions or cancels out charges made during this battery's operation. So like these chlorines from the salt are going to go to lithium, the sodiums are going to go to these chlorines that were made. Now all the charges balanced, battery can run just fine. Second question. Student adds the missing component to the cell, the salt bridge, and he finds the E degree, that's voltage. That's just, I don't even know where that comes from. that's the total voltage of the cell, is plus 1.54 volts. And it also tells us as a cell operates, silver plus ions are reduced. Use this information to do the following. Question A, calculate this half reaction. Now, what I've noticed is both these reactions are for reduction, the gaining of electrons. So we're going to have to flip one of these reactions because obviously one has to give off electrons, one has to accept it. So we're having to find the voltage for this. Here is how I would find that. I'm just going to, where is this thing? I'm just going to start a new page. So I know total voltage is equal to the voltage of my anode and the voltage of my cathode. Total voltage, it tells me, is plus 1.54. And we're adding these voltages together. Now it tells me that silver plus ions are also reduced. Oil rig, reduction is gaining. So this silver reaction is the correct one. This is written correctly. Silver is gaining electrons. That is going to be the cathode, so that's plus 0.8 volts, which I'll put in right here. So voltage of the anode plus 0.8. So what we need to do is a very simple equation. The voltage of my anode is going to be 1.54 minus 0.8. Voltage at the anode is positive 0.74 volts. We need to do one more thing, which is that this positive voltage is for an anode, it's for oxidation. The reaction as it's written is the reduction reaction. So I need to flip this, that the voltage of that chromium reaction is actually going to be negative 0.74 because the reaction as they write it is a reduction reaction, which will flip the sign. And we can qualitatively check that answer. If this voltage is negative 0.74, we're going to flip the reaction, we're going to flip the sign, we're going to get positive 0.74. We add these voltages together, we get an easy positive 1.54. Answer makes sense. So the answer to I is negative 0.74 volts. And then II and III, we're just going to skip. III, we might do later. Who knows? That is all that I will leave us with. Thank you for watching this recording. Have a good night.